So today I'm going to talk to you about pruning and recovery of machine learning models. And this might not mean much to you right now, but hopefully by the time I finish today it will. Machine learning models have become more and more prevalent and more commonplace in the last couple of years, right? A really obvious example is ChatGPT, which is a very large neural network. The example behind me right now is a toy example of a small neural network, which is a type of a machine learning model. These networks, these models, we can think of them as some sort of mathematical equations. We have these circles. They're called neurons. And we have the pathways, the connections between these circles. And we can think of them as parameters. They're actual numbers. They have values in this equation. And so this example behind me, its purpose is identifying between cats and dogs. It gets its input, in this instance, an image of a dog. It converts it into numbers, and it then inserts it into the equation. It does its mathematical calculations, and it outputs, this is a dog. But even though that is the purpose of this model, current machine learning models are aimed at much more complex tasks. Right? We want them to be able to generate text. We want them to be able to generate videos, to generate images, et cetera, et cetera. And we found out that in order to do these complex tasks, we need the models to be much, much bigger. And so current machine learning models are big. And not just big, they're very, very ridiculously big. Just so you have a number in mind, ChatGPT has over 1 trillion of parameters. And even though making those models bigger allows us to combat these tasks, it has obvious drawbacks. The first is storage, right? I have much more parameters. It takes more service just to store them. The second is electricity. The computer needs more power in order to calculate for these equations. And so the perfect solution, in a sense, would have been a small model, right? One that doesn't have these drawbacks, but one that is able to do these complex tasks. The obvious solution, in a sense, would have been to just train this small model, but we've seen in practice that it doesn't work. We can't have a small model that does these tasks well. But we still want that solution. And that's where pruning comes in. What is pruning? We've already said that models can be thought of as long mathematical equations. Because they're so long, they're billions upon trillions of parameters long, they have some redundancies inside of them. Some parameters might have redundant relations between them. So if you could just point out these redundancies, if you could just figure out which parameters cause these and just delete them from the equation, we will get an equation which is smaller, right? A smaller model, but one which should be just as good as the original model. And again, I have this toy example right here. I have these 3 neurons and the parameters, the connections between them. And if I could just identify the redundancies and prune them, I would get a small model, but one which should be good, just as the original. Pruning can be generally divided into 2 categories. The first is light pruning. In this example right here, I have the original dense model on the left side and a pruned model on the right. Some of you might even find it hard to see that it's pruned because we removed so little parameters. But a few are, just like the top middle parameter. And even though this doesn't save us much space, it is easy to believe that the equation that this pruned model represents is very similar to the original equation, right? Because we deleted so few parameters. So it should behave the same way. On the other hand, we have a much more aggressive type of pruning, right? We've deleted almost all of the parameters here. And so also it is very easy to imagine how this sort of model deviates very largely from the original model. And the problem is, with this sort of pruning, the aggressive problem, is that models which are pruned very aggressively, they're just plain bad. We might have an original model which is very good at its original task, but if we prune too many of the parameters, if we prune too much, the model that we get could be very bad at its task. So what can we do? Because we do want to prune aggressively. We want models which are smaller. That's our entire purpose here. That's where recovery comes in. What is recovery? After we've already pruned a model, we want to recover its weights. We keep the pruned parameters fixed. We do not touch them after we prune them, but we do allow for the values of the unpruned parameters to change in order to find a better solution. And so in this example right over here, I have on the left the original dense model, and it has one highlighted parameter, this line, who has the original value 42. We then prune it. We can see that a lot of the parameters were pruned, but this any parameter that remained unpruned retains its original value. And then we allow for recovery. In the recovery, notice how we do not return any of the pruned parameters, but we do allow for the unpruned ones to change their value. There are many current recovery methods, but most can be sorted into two brackets. The first, look at things in some sort of local environment. What does that mean? I can sort of divide the equation into segments and look at the segments and solve it only at those. So I start by looking at these three neurons. I solve the equation around these three neurons. I then move on to the next set of neurons, and so on and so forth. And I solve it. I get to some sort of solution, right? I recover. But it is easy to imagine why this solution might be suboptimal, since this entire thing is one giant equation. It's not three sets of independent equations. The second set of solutions, the ones that try to avoid these local environments, are computationally inefficient. They usually involve some sort of retraining of the model. This retraining uses over 1 million examples shown to the model tens of times. As you can imagine, that takes quite a while. And that leads me to our method. We believe that pruning causes a very specific sort of damage to the model. Pruning shifts its internal computations. And so in order to recover the model, we only need to sort of understand what shift should we shift them back to. And we can do that using two things. We can do that using a small set of examples and the original dense model as a teacher. We then teach the pruned model the way to shift back using the internal computations. We tell them to mimic them. And so we get a procedure which is both global, right? Because we look at the equation in its entirety, and also uses a very small number of examples. Like I've told you, retraining uses over 1 million examples. This can take 1,000, maybe a few thousands. And this is also very good in practice, not just theory. We have here the original dense model, and we have here its accuracy, how accurate it is at its task. And its original accuracy is almost 85%. We then prune this model. We do some sort of aggressive pruning. We get to 15% of its weights remaining. And we can see the accuracy absolutely plummets. It doesn't even get to 6%. This model is very, very bad. But then after using our recovery method, the number of parameters remain the same, right? We still have 15% of the parameters, but the accuracy climbs back up. It's now 78%. It's very close to the original dense model. And so the main takeaways, as I think of them, are the following. We've started by saying that we needed bigger models in order to combat more complex tasks. But using these big models, we have problems with that. We can't just train a small model from scratch because those don't do as well with these problems. That's where pruning comes in, but pruning also has problems on its own. More specifically, aggressively pruning shifts the internal computations, and that's where our solution comes in. In order to recover the model, the only thing we need to do is to shift back the internal computations, and that can be done using the dense model as a teacher and a small number of examples. And that's it. Thank you.